Hi everyone, it's me again today, February the 6th, our new daily challenge for today. Alright, let's take a look first. Any comments we received from previous? Probably, I can remember a comment on this one. Let's see if it's related to my comment. Probably not, most likely not. Yeah, I don't think so. Nope, that's fine. Alright, let's head right into it. Oh, it's binary tree. I like trees. Like C. Wow, so short. A question. Does that mean it's an easy question? That's weird. It's Saturday. Given a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. Wow, this is interesting. This is very, very interesting. Basically, it's just is that the rightmost branch? Is that what we're trying to do? Rightmost branch? Yeah, I guess that's the rightmost branch. So we just go right side first. We visit, go right, visit, go right, and visit, go right until we got to the end. And that's it. Yeah, I'm not sure if there's any trick in this, but that's how I'm thinking right now. We just keep going right. We visit the root node, then we go right, visit the root node, then we go right until we reach. Oh, I see the trick. No, it's not gonna work because yeah, let me just test this. As I was saying, I kind of realized, yeah, this probably not gonna work. For instance, if I have a 6 and a no, oh, okay, we have to go no first, and then 6, nope, I've got 2 no's, and then a 6, and then a no, right, like that. The 6 shall be included in the return. Yep, it's 1, 3, 4, 6. So it's not just the right, all right? It's just okay. So if a node, I have a left or right, then I go right. A node, if so we go right all the time if there are choices for left or right. However, if there's no choice, we just have to keep going. Like there's no choice, we keep going. This node doesn't have a right child, but it has a left child, so we keep going, and then we keep going, and then if there are 2, we go to the right, and then until we reach a point where there are no children at all. Yeah, I think that is the solution. So it's a little bit twist. Just a tiny little bit twist. I am confident. I probably won't even run a test and then just go right into it. No, I'm not gonna do that. You have to test every time. All right. So what do we do? It's going to return a list. So basically, we are going to write a recursion inside. So we're going to say result is a list. I'm going to store the value. Yeah. And then we're going to def a, let's call it DFS R, which means we can always go to the right. So we have a node, which itself is a tree node. And this one doesn't return anything. We're going to say if not node, if node, res.append node.val, and then if node dot left, so the left is not null, then DFS R, we go node dot right. Hold on. No, that's not right. If node dot left and node dot right, we go right. Elif node dot left and not node dot right, then we go node dot left. All right, and then the last situation is both both are no. So the left, right, both are true. We go to the right. Okay, it's actually not this. It's if no dot right. If right exists, then we go to the right. If right does not exist and left exists, we go to the left. If right and left both does not exist, then we don't go anywhere. And we're gonna just return result. So this one is a tree, which I do not test locally. We are going to run on here just to see. On this one, see if we can get it. We get nothing. Why is that? Oh, because he didn't run it. Come on, man. I have this problem all the time. I never run it. Good. We got one test case. Let's try another one. Which basically is to remove all this and then leave only 4. Yeah, I think this one should be good. And yeah, that's this. What else? I guess nothing. Some edge cases, like a single node. Okay, 2 nodes on the left side. Have to wait. Which is good. Empty node. Always test on empty node. What is my laptop? The laptop is making a lot of noise. The heck are you doing? Oh, I forgot what my laptop. My laptop is live streaming. That's why it's making a lot of noise. All right, submit. Oh, wrong answer. Oh, we got a wrong answer. All right. I think I saw it. I try not to see it because it's kind of like cheating, but I actually see it. Oh, I forgot to take into account this situation. That's right. Holy moly. Oh, wow. This is... Huh. Huh. Okay. Because this is going to be 1, 3, 4. Yeah, I got 1, 3. I think I know. So what we're saying is we have to... Damn. That means we have to go breast first? Because if we go depth first, right? We finish this, then what? Then we have to, what, go up? So every time we have to go the left side again, and we have to know if the left sides go lower, which is not going to work. So we have to go BFS. BFS, check this, BFS. We just need to know which one is the last one, right? How do we check which one is the last one on a row? Well, we can check by, I mean, it's a queue, so we push it in, and then pop it out, and then say the previous one is, and then we're starting with, that's a new one. We always store the previous one. Previous one, yeah, we always store the previous level, and then, not the previous level, we always store the previous, yeah, the last one. Hold on. How do we make sure that it is, so when we pop out, right, we pop out, and then we compare to the previous one, and then we know this is the start, and then we I'm thinking like, say, 1, right? 1 in, and then we get 2, and then we get 3, right? And then next round, 2 gets popped out. How do we tell that 2 is not on the right side? Well, we know 2 is not on the right side because the previous one level is different from 2. That means 2 is the first one, so we don't care. We update the level. And then 3 comes in, is the same level. We update the level. And then 4 comes in. And then when 4 comes in, 4 sees that the last one is different, which means the last one is on the right side. So we push this one into the result. And then this, and we push 4 in, and then nothing goes push in, we get 4 out. Alright, so 4 is already out. 4 is already out, and then 4 is empty, so nothing gets pushed in. We probably have to push none. We have to push none in. Wow, if we push none in, then we are wasting a lot of memory, a lot of time. But if we do it that way, say 4 gets popped out, but when 4 gets popped out, we can check this, right? That's the only time we check this. And 4 gets popped out, and we'll update it, and nothing else, which means this must be the last. So we always add that one. Okay, we might. All right, let's redo it. So yeah, I think the DFS doesn't work very well. All right, we're gonna use a deck to represent a queue, and the queue, come on, we will start with a root. So we're gonna do root.val and 0. So this is going to be node value and level. So that's going to be each one inside. And then, none of this. I'm going to say while q current val, current level is q.pop left, right? Q.pop left. Oh, we also need a previous value. Previous value is, doesn't matter, it's none. Oh, we need previous value. So if I pop it out, now to say if, oh, why your current value has to be node, dummy, has to be node. So we're going to say node, just a node level. If node.left, q.append, node level +1. If node.right, q.append, node. What are you doing, node? Node.left, node.right. If not root, return res. That's just for edge cases. And then this was also level +1. All right, so we pushed both in. Now we're gonna check. We're gonna check whether the current level and the previous level. I do need previous level. Pre-node and pre-level is none and -1. So we are going to check. Say if current level is not equal to previous level, that means we are going to push the previous node. So res.append and pre-node. then can append pre-node dot value. And then after do this, pre-node and pre-level equals current node and current level. Every time when check, and then when 4 comes out, and looking at this one, when 4 comes in, left, right, nothing gets pushed in. Level is not equal to previous level, and the previous node is 3, so 3 gets pushed in, and then now pre-node and pre-level is this, and then we get out, and we always rest dot append pre-node dot val. That's the last value, and we return rest. All right, this is the BFS version. Let's see if this test cases pass. This one passed. Now we have to see if this one passed. Yeah, I can't believe I didn't think about that test case. It's so obvious that you will have all these different types of things going on, but it's just, you know, unimaginable that I would forgot to take into consideration the other possibility. All right, I think we are good, and we are going to submit. Yes, we got it. We got it. Let's see. We are at 19% ranking. Which is 40 milliseconds. What's this? 30 something? 32? That's about the same. I won't worry too much. Did we do anything that make things a little bit difficult? Not as efficient? I mean, one thing we can improve is, I mean, we have a deck, so we can peek on the top of the deck. If the top of the deck is the same, then we pop it out and push the current one. Hold on, what are you saying? No, you cannot. You cannot. Well, yes, I can. Not the top, but the tail. I actually can peek at the tail, and if the tail is the same, I just pop it out. Keep pop until so if the tail, so I push in the tail, right? If it's not the same, I push in the tail, and if it's the same, I pop it out. I push in a new one, and I keep doing this, so eventually, the queue will contain only one. That's actually a good thought. So every time I pop out, I can just add it to it. Let's try it. Let's try it. I'm not sure if you guys understand my new solution, but the new solution is like this. When we pop it out, we immediately append node.val, and then if the left, right, and then we're gonna also check if it's the left, and then we're gonna check if that the left, hold on, if left exists. Now we're gonna check if the tail of it. So if deck, not deck, we have a queue -1 and 1. If that is not equal to the current, if not equal to level plus, hold your horse. Hold your horse. If the current tail of the queue is not the same, the level is not the same as the current level, then we No, actually it's like this. If it is the same level, then we do q dot pop, and then we do this. So it's the same as here. That means every time when we push in, we always push in the last value, and we don't need to do this. We don't need to do this. Certainly, we don't need to do this. Let's give this a shot. Here, change the solution. About the same length. Run this. Deck index out of range. Oh, if q then, yeah, if q. So it has to also if q, and same here, if q, and now we run it again. Runtime error. Prenode is not defined. Did I use prenode? Oh, I probably don't need this. Okay, this one passed. How about this one? Waiting for enough, sufficient amount of time before we do it. It passed. How about the one that I failed? This one. It does not pass. Why does it not pass? Let's see. So with this, we pop this one out, we add it in, and then if it has a left, if Q, so if not Q, Q append this. Now we go to right, if Q, and then the level is the same. Pop this, add this. Now next level out is just this one. Record. Ooh, this never gets pushed in. This never gets pushed in because we popped this one out already. Huh. Guess we cannot change the original plan. Interesting. Yeah, that's right. We cannot do it this way. We cannot pop. Or we cannot just pop this one because it might have some connections down. Alright, this is not going to work. It's not going to work. Let's go back to the old one. Can we restore? No, wait. On this one. Last submitted code. Yeah, replace. Yeah, let's get back to this one. Yeah, so we do have to go through each and every node. Well, not each and every node. We set a previous node to determine when we identify the new one. Yeah, we cannot keep, because that solution is the same as the DFS, where we always keep to the right. We don't care about anything on the left, but we have to care about things that happen on the left. Yeah, there's no way around it, at least from my perspective, but we are going to check. See, this is a medium question, I think, most likely. It's a medium question. Okay, we don't have a solution, but let me write my understanding here. You have actually a lot to write about. I initially wanted to use DFS and only going down on the right branch. This strategy looked promising at the beginning, but I failed a test case where the bottom level only has one node and it is on the left branch. Thus, DFS going down the right branch is not going to work. However, we can use BFS to traverse the tree. The only thing we need to take care of is to identify when the last node on a level is encountered. The current solution use a pre-node and pre-level to record the previous node encountered. This way, when the current node's level is different from pre-level, we know that pre-node is the last node on pre-level. We just need to push the pre-node's value to a result list. ON, because BFS, and we have, 40, right? 40 milliseconds, and it is 19% ranking. No es bueno, pero es suficiente para mí hoy. Es primera vez que había hecho esta pregunta. Vamos. Vemos otras soluciones. This is Java. This is modified pre-order traversal. So you can still do pre-order traversal. BFS level, that's the one I use, most likely. Okay, I think we can do okay, well, what are we saying right now? Recursion with level. Oh, we do a level. Okay, so this is a tree, right and left. So it's just regular tree, right and left, and yeah, I saw it. This seems to be the key. Result, the size is smaller than a current level, which means we are on a new level, because that's correct, because the size of the result list is the same as the depth of the tree, and at each level of the tree we have to push in a value. That means if we are at a level, right? If we are at a level, whose depth, whose level is larger than the current size of the result, which means we're on a new level, right? We're on a new level, and then we push the roots value. Why we push the roots value? Because if we are on the new level, so this says we're on the level, right? Yeah. So we're on this level, and we push this value. Then we go right, and then we go left. So we go right, and we keep going right if we go right, and this is the right level. Like at this level, so I am at the current level, which is larger than my size. That means I'm at the new level that the result list has not encountered yet. Therefore, and I'm also going right. I'm going right first. So when that happens, I am the right choice. So I push my value in. Now, it will happen that after I push my right value in, and then there's nothing more to go, so we have to go back when we go left. So when we go left, now we check if the current level, if the size is equal to my level, that means I have already visited this level. Oh my lord, this is great. This is brilliant. This is brilliant. Wow. That is the trick. Well, you have the stack. Yeah, it takes a stack space. So this is fine. Doesn't matter. Yeah. Right now we at it first. Yeah, this is wonderful. Wow. Holy. Holy. Estupendo. Estupendo método. Esto es. Estupendo método. Brillante. Muy brillante. Ah, vamos a probar. Vamos a probar a mí mismo este método. Recursion, right? Recursion. So what we're gonna do, let's not look at all. Don't refer to it. Don't refer to it. All right. So what we're gonna do is we're gonna do DFS. We're gonna have a result. That's true. And def DFS. We're gonna have a node, which is a tree node. And we say if node. All right. And then what we're gonna do is we're gonna check. Oh, wait. And I also level. So if node, we're gonna check if level is large, then rest of size, not rest of size, it's len rest. Yeah, if it's larger than len rest, then rest dot append node dot val, and then we're gonna go DFS node dot right. We go right first, level +1, DFS node dot left level +1. That's just brilliant. We do DFS root at 1 and return rest. Oh, maravilloso, maravilloso. Sin duda, maravilloso. Muchísimos maravilloso. Good. Otra vez. No hice. Ah, brillante, muy brillante. Como esto. Ah. Oh. Esto es la solución con 32 milisegundos. Eso es la mitad. La mayoría. Sí, la mayoría. All right, this is good. This is good. A brilliant recursion solution. I thought DFS is not going to work. Well, it won't work the way I was thinking about it. but this way, but this method supplied by, let's get the link. Oh my god, this is brilliant. Supplied by this works perfectly. Why, really perfectly. The key insight is that the length of the result list is the same as the depth of the tree, and at each level of the tree only one value can be pushed to the result list. Therefore, we can use the size of the result list to determine whether we can compare, not use, we can compare, I cannot fit here, we can compare, meter, we can compare the size of the result list and the current level of a node to determine whether the current node should be pushed into the list. If the current node, which always prefers the right branch, which is always right branch first. If the current node has a level larger than the size of the current list, that means the current node is on a new level. And since it is also on a new level, and since it is right branch first, I shouldn't say like that. As a new level, thus it should be pushed. Its value should be pushed to the result list. When the traversal hits the left branch, the comparison between the level and size of the result list also helps to identify any left child that is on a level not reached by the result list. Still ON faster. 32 milliseconds, we have, I think it's 72% ranking. 71% ranking. Alright, this is good. It's good. Let's see, Mr. Parkman. A right view of both right and left subtree, then combine them. Got right view, also right view, and then root del val plus right plus left, then right. Oh my god, this is too complicated. So I got a right view of this, got a right view of this, and then what? A root del val plus right plus len right. Makes sense. Makes sense. First comes first serve. Yep, that's the same method. Iterative, level by level. Okay, why is so much easier? root level is okay. It does do this, and then what? Oh my god. For kid in left or right, if kid, and then for kid in this, if kid, so for kid, and for node in level, all right, for node in level, huh? For node in level, okay, for node in level, and then for node in level, and for kid in the left and right, if kid, now we put kid in it, and then level is the new. Wait, how is this one correct though? We always take, oh, oh, ah, not a universal queue, but just, oh my goodness, this is good. The reply. Oh my god, yes, I was, but you're faster. But I want to try this one as well. Yes, this is I won't say it's it is easier to implement, that's for sure. All right, so we have the root. So what we need to do is we get the level, right? We get the entire level each time. My goodness, this is good. All right. So what do we do? Level is if not root, return empty. That's fine. And then the rest is this level. All nodes in the level. Yep. While level. Rest dot append level -1 dot val, and then for node in level, and then for node in level, so we have a node, then for child in node dot left, node dot right, if child, and then child. So I think let's put this, and then put this level. Not sure. I never used this syntax before. This is how I understand things shall go, but I'm not 100% sure if that is correct. Hold on. Can I mean, We should put this at the end, right? And then say child. Then we'll return the rest. Not sure, but we're gonna try. It's a good method. Yeah, compared to this one, my BFS looks like poop. Certain poop. Node is not defined. I think it's my list comprehension. So are you saying that it's the other way around? So I see child for child in node, and I say node is not defined. Okay, it doesn't make sense, which means we have to do so it's gonna be child, it's gonna be for node in level, right? For node in level, and then for child in this if child. Did you click it? Oh, this one works. No, it says. Yeah, I think we can submit. Nice. All right, so it also helps us understand the list comprehension a little bit more. So my thought is we always put the top level out at the end and the second level at the front, but apparently it's not true. The top level, so it basically you write out how you want to write out and without list comprehension. So we always put the top level here. Top level is at the front, and then the second level is here, and then you put the thing you actually want the list comprehension to produce, and you also put in a condition here. So this is the solution. I call it the better, el mejor BFS. Provendito, is that how you spell it? Provenito? Oh, come on. Provide. Prover. Proveito. Yeah, I think it's proveito. Proveito por Stepan Mr. Pacman. I know who he is. He's a very good one, Mr. Pacman. Pacman. I want to also copy his link. It's here. It uses sort of a mejor BF, sort of. It's sort of a BFS. Sort of BFS, but it basically expands each row, each level of the tree, and take the last value of each level. Very straightforward, but works pretty well. Also notice the what is it? Nested list comprehension ordering. The top top level 4 comes first. When 32 milliseconds, 71% ranking. Oh. All right, I think that's it. 3 solutions, good enough for me. We covered DFS, we covered BFS, and we also covered these 2, and we also used our own, whatever BFS that we have come up with. All right, that's it. That's it for today. Gracias por escuchar o ver. Hasta mañana. Hasta mañana. El domingo espero que tendremos un problema difícil. Pero voy a hacerlo. Hasta mañana.